So today we're just going to take a look at this quick hash table problem. It's really just an expected value issue. And we're just wondering how many slots we're going to check if we hash some element x into a hash table with only m minus 2 open slots with linear probing. So remember that linear probing just means that if we have a collision, we check the next guy, right? So already that should kind of help you out here. Notice that when I say m minus 2 slots, that really means that we have m slots, but 2 of them are already occupied, right? And the first thing we're going to do is we're going to assume independent uniform hashing like we usually do, which just means that the probability of collision is 1 over m, or in other words, the probability that anyone hashes to anywhere, like to any of the m slots, is 1 over m. Now, like I said earlier, since we're doing linear probing, it simplifies our problem a bit, right? We can either access 1, 2, or 3 slots. And think about that for a moment, right? If we access our first slot and we're good, we're done. That's accessing 1 slot. If we access 1 slot and we have a collision and there's no one occupying the second slot, then we access 2 slots. However, if we access 1 slot and the next guy is occupied, then we'll access 3. But remember, we can't access more than 3 because there's only 2 occupied slots. So those are our 3 cases. And right now you could pause this and solve this yourself now that we've simplified it to that. But otherwise, let's just start with p of x equals 1, where x is the number of accesses that we do. Now, obviously, you can think about this in a variety of ways, but I think the most straightforward way is to say, okay, there's m minus 2 places that will allow me to go with 1 access, and there's m total choices, so I have m minus 2 over m. And you could try to solve p of x equals 2 next, but I'm not really sure how to do that intuitively, but I do know how to solve p of x equals 3 now. So we know that that happens with probability 3 over m squared, and the reason for that is because we're just taking fundamental properties of probability and multiplying these 3 independent probabilities because I have my uniform hashing. So just think about it like this. This event only happens when I have 2 elements next to each other, right? And then I insert that third element in the first of those 2 elements. So the first element I can insert anywhere. So that's why I have m over m, because I have m good choices and m total choices. The second element I insert, I only have 3 good choices. Now the reason for that is because if I insert them in front of my first element that it's inserted, I'm good. If I insert them and I have a collision, I'm also good because I'll insert them next. And if I insert them after, I'll also be okay. In any of those cases, there's 2 side-by-side elements. And then my third element only has 1 possible place that will give me 3 accesses, which is colliding with whichever the first of those 2 elements is, doesn't matter. So that's how, if you simplify this, it becomes 3 over m squared. So now, it's easy to find p of x equals 2 because like I said earlier, there's only these 3 cases. So we just use the law of total probability, we subtract our stuff, and that's that probability. Now, there's a last step here that I'm not including because, it's pretty standard. You just find the expected value of x, and that will give you, the expected number of slots that you will access, right? So you multiply our first probability by 1, this second guy on the screen, p of x equals 3 by 3, and this last guy by 2, and you add those up. And yeah, we're done.